So I forgot to go over the scoring guidelines for this. So I want to go over the scoring guidelines. So just to give you an idea how you can look for this stuff on your own. So remember, this is a free response from 2009. So all I did was I went into Google and typed in 2009 scoring guidelines, and it brought up the AP1 calc right off the bat. Now maybe it brings up AP stats, or look, here's AP human geography. So you might have to do a little bit more than that, but basically it pops up pretty easy. So I pop up, here we go. This was number 1, I think. Yep. So let's kind of just go through and talk about what we had and what let me see if there's a way that I can bring our work. We'll try our best. So let's talk about it first. We said, so let's see, they said this, so this is a 9-pointer, 2, 2, that's 6, 2, 2, 2, 6, and 3 more is 9. So in part A, to get to 2 points, you needed the answer and you needed the units. Now, the answer, did we show you have to do a little bit more. Look, this is what they mean by the answer. You have to actually not just write this down, you have to kind of show a little bit of what you're thinking. I don't think if you didn't include this, I think you wouldn't get it wrong. Now, what we did, so you could either ignore this or this. I think you could ignore one of them, but not both of them. That's why when we did it, I encourage you to just do both. I'll try to zoom. Maybe I'll just really zoom in. Maybe that'll be the best way. So if you see how we did it, we defined A of 7.5. Then we did that was the same as the derivative of velocity, which then turned out to be our answer. So we did it graphically, remember? Now, if you don't have a graph and you just have a function, then you have to do the difference quotient. And then we also remembered our units, so we would have gotten both points there. For this, 2 points, the meaning of the integral and then the value of the integral. So let's see what they said about the meaning. They said is the total distance in miles. There's that sneaky little units. Now, we do units most of the time. It's pretty easy when we're talking about t equals, or if we get v of t equals, it makes sense to write the units after that. But this one was a little bit sneaky, so you had to slide the in miles in there because you're talking about distance. So this integral, absolute value, had to be the total distance in miles that she rode from 12 minutes, from 0 times t equals 0 to 12. And if you look at that, we had that little reminder note in there that don't forget your units after you're talking about the distance. So in these story problems or these free response questions where you have units, anytime you talk about a measure, put units afterward. Traveled from time t equals 0 minutes to 12 minutes, okay? And then the actual value of the integral, notice they did it too. They wrote out, now they wrote it a little bit differently than we did. They decided to break it up into the sections. We did all that by looking at it graphically. So we just had all those sections written up above and then added those together. I kind of like the way they did it. But anyway, we ended up at the same place. We showed our steps. We didn't just magically end up at 1.8. Let's see, point 3, answer and the reason. So the answer was Karen turns around to go back home at 2 minutes. And it's because her velocity changed from positive to negative. There's that little reminder that you have to talk about, not just switch the signs, but it has to say it switches from positive to negative. What did we say? Karen turns around to go back home at time equals 2 minutes because her velocity switched from positive to negative at time equals 2 minutes. Did they say that again? No, we said it. This is the time. So they said it that way. This is the time at which her velocity changed. And then lastly, what do we need? 3 points for this last part. Larry's distance from school, the integral, and the value. So that was this, the integral, WT. And then remember, we could do that on our calc. So that should be a real easy 2 points. And then Karen's distance from school and the conclusion was the other point. So let's see, what did we say? We started off talking about Karen. We showed all of our work, boom, 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 added it up. Then we did Larry's on the calc, but we still wrote it all out. And then we made a little argument, a little nicer argument than they made. I think Corpy said that when they printed this, they had lower expectations. They actually have more expectations now than they did back then. So this little argument that 1.4 is less than 1.6, they didn't even score back then, but he felt they would score that now. So since 1.4 is less than we showed, that was our conclusion that we got. One other interesting thing that you can look up is you can look up how kids did on that. So on 2008, question Oh, this was 2008. I want 2009, don't I? Yeah, what's 2008? 2008, is that the one I'm doing next? Yeah, that's the one I'm doing next. So let me do a quick search. 2009, AP Calc, scoring, what did we call that? Scoring stats. Oh, I didn't even spell scoring right. Luckily, Google takes care of that for me. 2009 scoring stats. These are still. Okay, I'm talking about how easy it is to find this. I found it just a couple minutes ago. Grade distributions. I don't want the scoring guidelines. I want the scoring statistics. Free response 2009. Free response questions, AP Calc, scoring AB. Grown. Oh, is it at the bottom of this by any chance? Nope, of course not. Well, anyway, you could find it somewhere. I was just looking at the darn thing, so I don't know where I lost it, but I lost it. So there's an example though of the 2008 one you could look up. We're going to talk about that after we do the next example. Okay, so moving on. We are now talking about 2008. No calculator. Oh, that's why. He only did it after this one. I don't know where that other one is. Anyway, a couple of things to highlight, things that you look at that should jump off the page to you. No calculator. So that's bad news. I'll do that in pink. Be sad about it. This would be on the no calculator section. Good news is it's talking about a particle. So I like that. Let's see what are some things that move my calc out of the way. What are some things that we notice? So our particle moves along the x-axis, so its velocity time t from 0 to 6 is given by the differentiable function. There's a hint. Let's circle that and leave ourselves a little note. If our function is differentiable, then it must be what? Continuous. So that's implied. V, whose graph is shown. So here's our picture. The velocity is 0 at time. So the velocity is 0 at time 0, 3, and 5. So those are all things that I think are worthy to highlight. So here, here, and here all have a velocity of 0. So V of 0 equals V of 3 equals V of 5 equals 0. That's probably going to come into play later because what could happen when our velocity is 0, you could switch signs. So those would be important places when we're talking about the position or what direction our particle is moving. The graph has horizontal tangent lines at t equals 1 and t equals 4. So what does that mean? That means that v prime of t equals 0, v prime of t equals 0, which also means I can actually put the number in there. A of 1 equals 0, v of 1, and then this was v of 4. Or v prime is the same as the acceleration. The acceleration at 4 equals 0. So those might come into play later on. They obviously will because they told us about it. Well, I guess not obviously, but they probably will. And then they told us that the areas of the region are certain values. So they do this sometimes when they don't want us to have to calculate the integral on our own. So the areas of the region bounded by the t-axis, boom, and the graph v, boom, on the intervals 0 to 3, 3 to 5, 5 to 6 are 8, 3, and 2. Remember, this word respectively means that the order that this is written corresponds to the order that this is written. So this area is 8. Well, where is that? I'm going to be a little bit careful. I'm going to write it as -8 so that I remember that that's actually below the x-axis. And then if I need to use it, I'll make sure it turns back into a +8. They're just talking about areas. So from 3 to 5, the area is 3. I don't need to sweat that one. And then I don't like that they have this. I'm going to highlight this section, kind of separate it. And in that, we have an area of -2, because that's underneath the x-axis. At time t equals 0, the particle is at x equals -2. So from that information, we now know that at time 2, the particle is at time t equals 0, the particle is at. So that's a position equation. So that means x of 0 is equal to -2. That's talking about my position. That's not talking about my velocity. Because if you look at the picture here, that means, what's our velocity at 0 is 0. It's not at -2. So look at all this information that we found before we even dug into one question. This is just interpreting the hints so that you have something to work with when you actually start to read the questions. Okay, so another thing that this sometimes is helpful to think about, this means our particle is starting at -2. If I now draw, this is not this graph. This is not the same. This is the function x of t. This is the straight line that the particle is moving along. So this is a position equation. Our particle is starting here at -2. So our particle begins here. At time 0, the particle is at a distance of -2 from 0 to the left of 0 by 2. All right? Okay, so now 4 times, find both the time and position of the particle when the particle is furthest to the left. All right, now if we're talking about the furthest of something, the furthest left, the highest, the lowest, these are all examples of which one of our theorems, which one of our VT theorems. Okay, intermediate value theorem, that finds the number that guarantees a number in between two other numbers. Then we also had the MVT, that guaranteed that there was some slope on an interval that was the same as the slope of the whole interval, the average rate of change for the whole interval. And then we also had the one that has to do with the biggest or smallest. This is what we call the EVT, the extreme value theorem. We want to find the farthest. So my particle is going to be the farthest to the left, so my particle is here. When I'm going farthest to the left, I want to see what values are we looking at over here. As we move farther and farther left, what kind of numbers are we looking at? These are negative, smaller, smaller, smaller. Now, our particle doesn't move left forever. It eventually comes back to the right, as you can see from our picture. But we want to find the spot where it's furthest to the left. So that would be what value is. We're looking for the minimum of our position. So we're trying to find the smallest value possible of our position function. Okay, so for us to figure out the extreme value of position, we need to figure out, if you remember the extreme value theorem, that's the one with the candidates test. So let's go down here. We'll highlight part A, the extreme value theorem. So we have to list candidates. Where do the candidates come from? Well, one place. Let's see if you can remember. Pause and try to write down how you find your candidates. Hopefully you wrote endpoints. And then what's the other one? Crit values. Okay, so when endpoints, that's going to be pretty easy. So we can list our endpoints right away. Our endpoints are, I'll do a dot dot. Endpoints occur at t equals 0 and t equals 6. T equals 0, t equals 6. Those are our endpoints. Crit values are a little tougher. When do crit values occur? What are the two criteria for something to be a crit value? A crit value occurs when, in this case, let's just use our variables. What variables? We have v. When v prime of t, wait, is it v prime or? No, it's x prime. We're talking about position. When x prime of t equals 0 or dne. And so for us, we're not talking about what is x prime of t. What do you know about x prime of t? X prime of t is the same as velocity. And so those are a little easier to figure out. So let's now use this to jump up here and try to figure out places where this occurs. And there's some of these hints that some of the givens are going to be used here. So when does our velocity ever equal 0? Well, they told us this is a graph of velocity. Where are the places that the velocity is 0? Well, since this is a picture of velocity, the velocity is 0 at those 3 locations. So we've got time equals 0 again. We've got time equals 3. And we've got time equal to 6. Is our velocity ever undefined? Well, no. Look at what we said up here. Right off the bat, they told us that the x-axis is given, the particle moves along with a velocity that is given by a differentiable function, therefore continuous function. So there are no places that our derivative would equal 0. Sorry, our derivative would equal dne. All right, so now after we have our candidates, we've got to figure out which number is literally the smallest or which one is the biggest. So this is a candidates test. I'm going to go in order, so we would need to figure out, okay, do I want to find x of t or v of t? I want to figure out when the particle is farthest to the left. So that's going to occur when its position is the smallest. So I want to figure out what the position values are. So I want to know what's x of 0, what's x of 3. Oh, shoot, I didn't complete my list over here. Sorry, I missed 5. Why did I say 6? That was wrong. It was 5. So those are the 0, 3, 0, 3, and 5. 6 was my other endpoint. So I need x of 3, x of 5, and x of 6. All right, any of these, how would you figure these out? Let's start off with x of t, x of 0. X of 0, what does x of 0 equal? -2. How do we know this? It's given. Game over. That one was easy. Now we want to figure out what x of 3 is. So x of 3, x of 3 is, you can calculate this, so I need to know its position. We have a picture of velocity. If I want to use the picture of velocity to figure out where my position is, what would I have to do to velocity to work my way backwards to position? Well, hopefully you said integrate. So as I integrate this, x of 3, all right, that's going to be the integral from 0 to 3. But wait a minute. If I just integrate from 0 to 3, that would tell me how much my particle is what between 0 and 3. That's how much that position has changed. It's its displacement. So what do we need to know first before we can figure out how much we've changed? We need to figure out where we started. So where did our particle begin? Our particle began at a distance of -2, and then from there, we added on some change. That's the integral from 0 until 3 of v of t dt. So that's -2 plus, what's the integral from 0 to 3 of vt? So this is where, do I want the negative or get rid of the negative? Pause if you don't know. Think about it. I want the negative. The integral should be negative because we're just integrating. We're not asking for the area. We would have to adjust the integral if we wanted to know the area. So we would get -2 plus -8, which is -10. Let's move on to x of 5. If I just integrate, what I wanted to do when I first did this problem was I integrated from 0 until whatever. It's no good because that would only tell me how much my particle has been displaced over that time interval. I need to know how much it started and then where it was displaced from there. So we start at -2, and now I want to integrate from 0 until 5 of v of t dt. So that's -2 plus. So I can't go all the way from 0 to 5 right away. I have to kind of break it up, but I can just write those pieces down separately. So the integral from 0 to 3 is -8, which we just did, plus then we want to add on the 3. So that would be -8 plus 3, which is -7. And then finally, we need to calculate x of 6, -2 plus 0 to 6 of v of t dt. So that would be from -2 plus, now I'm going to go all the way to 5 because we already calculated that. And no, I won't. Let's just write it out. -8 plus 3 plus -2. So that would be what? -4, -12 plus 3 would be -9. Now we want to take these values, put them back in our candidates test. That's -2. That's -10. It's -7. That's -9. So those are our possible extreme values. Obviously, who's the extreme? So who's the, which extreme do we want? There are two extremes. This is one extreme. That's the biggest number. That's the smallest number. We want the minimum. So we want the smallest number. There we go. Still not done, because the question was, we would need to find both the time and the position of the particle when it's furthest to the left. Our justification is all of our work here. We don't really need to do a ton of justification, but we do need to have a little bit of a write-up here at the end. So I would try to say it, I always try to say back to them what they said to me, or what they asked me. The particle is furthest to the left at time t equals 3. We don't have units, do we? I got a little nervous about units all of a sudden. No, there's no units, so that's good. The particle is furthest to the left at time t equals 3. Done? Read the question. Both time and position. So we get the time, we need to indicate the position. The particle is furthest to the left at time t equals 3 with a position of x of 3 equals -10. X was our position equation. 3 represents the time. -10 tells you how far. So if I was going up here, our particle would be moving back from 0 seconds to 3 seconds. Our particle would move back here to -10. Then from 3 to 5 seconds, our particle would move forward to -7. And then our particle would move back again to -9. Kind of squeeze it in there. But that's kind of how our particle bounced back and forth. That makes sense because velocity is negative, so it's moving to the left. Then it moves to the right for a little bit, and then it moves to the left again. All right, let's try the next one. So part B. For how many values of t, where t is between 0 and 6, is the particle at x equals -8? Whoa. Does this jump out to you? Do you see it? Do you see it? It took me a second. I hope to get better at these the more I do. And that's how you got to think about it too. For how many values is something at a certain value? That's a what? That's the example of what? Do you see it? This is definitely the IVT. So it's saying, is there a place, how many times does this thing equal -8? Well, we're trying to prove the existence of a point. So for us to try to figure out a position value of -8, that's the intermediate value theorem. So this is how I wrote it up. I started off just trying to do my old intermediate value theorem language. So if you don't remember that, go back and look up some of that or think it through. So everybody should be able to get the first part of the intermediate value theorem. Since V is differentiable, then V is continuous. Remember, we have to prove continuity in the intermediate value theorem. That's it. We don't have to prove differentiability. We have to prove continuity. But we know differentiability, therefore we're continuous. Since V is differentiable, then V is continuous. Now we have to make a bunch of arguments on where our position equals -8. If I go back to my little graph up here, how many times do those back and forth arrows cross -8? Or I could go to my candidates test. How many times do these values cover -8? How many times does -8 fit in between those position values? You should see that it happens 3 times, but we need to make the argument based on the intermediate value theorem. So remember, after we proved continuity, then we did that stuff with the less thans and with the middle and by the IVT type of thing. So since, we could write also, but since I'm going to do this, it's kind of repetitive, but I'm going to do this every single time. X of 0 equals -2, which is, nope, I said less than. It should be greater than -8, which is greater than -10, which is equal to X of 3, comma. So that proved that there's one time that we hit -8. Now I need to do it for the next section. That's between 3 and 5. X of 3 equals -10, which is now less than 8, which is -8, which is less than -7, which equals X of 5. And look, you should be pausing. If you feel like you can do this without just watching me do it, you should pause. And X of 5 is equal to -7, which is greater than -8, which is greater than -9, which equals X of 6. Then, by the IVT, how do I want to say? Do I want to say, I'm just going to jump, I was going to do a there exists here. I'm going to try to jump right to this 3 times thing. Then by the IVT, there exists 3 values of X from on the interval 0 until 6 such that f of x equals, dang it, I don't want to use x anymore. T such that x of t equals -8. Something like that. Something like that. I think we did pretty good there. It's not. We're going to look at the scoring guide in a minute, but I like that. I think that looks good. All right, let's take a look. Next up, what do we got? On the interval from 2 to 3, okay, I'm looking at my picture from 2 to 3. The speed of the particle is increasing or decreasing. Uh-oh, speed right off the bat. That jumped out to me. Did it jump out to you? What do we know about speed? Is speed velocity? No, speed is absolute value of velocity, first of all. Right? Speed is just how fast you're going. Doesn't matter which direction. And then when is speed increasing and when is speed decreasing? So there's 2 things that you have to look at. It's not as simple as just looking at this or looking at the speed, the velocity. You have to look at 2 things. For the speed of the particle to be increasing, the velocity needs to be, the velocity and the acceleration need to do what? Same signs. For it to be decreasing, they have to have different signs. I'm not going to write a ton here because we're going to write more of it up in our argument. So there's a quick review of speed. So let's take it down to this piece. So part C. On the interval from 2 to 3, the speed is increasing, decreasing. Which one? Well, this one's pretty easy. So let's start off by making our argument again down here. speed is increasing if v of t and a of t equals v prime of t have same signs. And then decreasing if v of t and a of t, which equals v prime of t, have different signs. And I don't know if you'd have to write all that up. As long as you make it, you wouldn't have to write it up. As long as you made a good argument, you'd be good to go. So what's our argument? What is v of t? From 2 until 3, v is negative, but v is also increasing in that section. So in other words, v prime of t is positive. So is our particle speeding up or slowing down? Particle's slowing down. But we want to say it in the language they use. They used increasing or decreasing. The speed of the particle is decreasing because v of t is less than 0 and a of t, which equals v prime of t, is greater than 0. I am pretty sure you could get away with saying v is increasing here if you wanted to. If you wanted to say v was increasing, that'd be fine. Those mean the same thing. And then last part here, during what time intervals, if any, part D, during what time intervals, if any, is the acceleration of the particle negative? All right, so when would the acceleration be negative? Let's write a little note about that first. The acceleration is negative if what is true? Acceleration is negative if what is true? If v prime of t is less than 0, or we could say v is decreasing. So that's the rationale, that's our justification. So let's use that now in our picture. Where is the places where v is decreasing? So it looks like from 0 down there, then it increases to there, then it decreases the rest of the way. So this is a pretty easy one. The acceleration of the particle is negative for all, what variable should I use? I should use t. That's an element of, okay, where were the places? So this decreases from 0 to 1. And then again from 4 to 6. So I need a union. 4 to 6. Because, why is this true? Because I'm going to say because v prime of t is less than 0. Or v is decreasing. Either one of those would be fine. All right, let's see how we would have done. Let's check the scoring guidelines. So this one I do actually have up and ready to go. So as I look at my scoring guidelines, so I typed in 2008 scoring guidelines, first thing that popped up. If you wanted to, you could type in 2008 question 4 AP Calc, something like that. That's where I'm getting this information. Okay, let's see. What did they say? We had to, number 4, 2, 3. There it is. 3, 3, 2, so 6, 7. This one's only, oh, no. There's one there. 3, 6, 9, 9 points. So we did identify t equals 3 as a candidate. Did we do that? Yep. T equals 3 was on our candidates test. We considered 0 to 6. The integral from 0 to 6, yep, we got that in there. We considered that distance. We could also, I think this counts too, just writing that as a candidate. And then our conclusion. So let's see what their conclusion are. Said the particles furthest to the left at time t equals 3 with the position of x equals the particles furthest to the left when the position, yeah, baby. Okay, down here, the positions, number 1, positions at, so we had to identify the positions at 3, 5, and 6. So this one's kind of nice. I was looking at the video on this. Did we actually do that in part 2? No, in part B, I'm sorry. No, we didn't. But actually, we did kind of. I guess we could argue that these values, we indicated those there, sure. But we already did it up in part A, so we don't have to do that again. So actually, I think we earned some points in part B in part A. The description of the motion. This one, I don't know if we did a good job with this one. I mean, I could say that it's differentiable. Maybe we should have said something like the particle moves left and the particle moves right, then the particle moves left again. I wonder if that's what they mean. What they say. The description of the motion continuously and monotonically, whatever that means. And then our conclusion, that's our IVT. See, they use the IVT there. And we definitely did the same thing. So that part, I think we'd at least get 2. I don't know about description of motion. I wonder if just us saying that velocity is differentiable and then velocity is continuous, that we'd be good to go. And then identifying all those values. The speed is decreasing, just 1 point for the answer. Since on the interval v is negative and v is increasing, I said that because v is negative and v prime is positive, means the same thing. Those are definitely the same. The acceleration is negative on the intervals from 0 to 1 and 4 to 6. So did we say 0 to 1 and 4 to 6? 0 to 1 and 4 to 6 because velocity is decreasing. Velocity is decreasing. I said velocity prime is negative, means the same thing. All right, let's try to squeeze in one more here. My math voice just got a lot jump for joy. Why did my math voice jump for joy? Calculator permitted. Yay, we can use our calc if needed. A zoo sponsored a one-day contest to name a new baby elephant. Zoo visitors deposited entries in a special box between noon, which they called time equals 0, and 8 p.m., which they called time equals 8. The number of entries in the box, hours after noon, is modeled by the different. There's something I want to highlight right off the bat. So there's really only one thing that I've seen so far that is important to me. This is differentiable, therefore continuous. So that's a help. Function e equals 0 to t. Values in hundred. Here's another thing. What is this? Units. Units. So you're gonna, some of these points will just be based on whether or not you can write down the right unit. Now, you want to write the right unit. Let's say you can't figure out the problem, but you want to at least get a couple points. You can write the unit, but put some number in front of it. Now, you put some number in front of it. You can't just write the units down and expect to get the points, but you could make up your own answer and then write the units and get some points for that. So the values of E of t are shown. Use the data in the table too. Oh, wait. I forgot. I wanted to go back and look at the scoring guidelines or scoring statistics. So that one that we did, remember 2008, number 4, right? 2008, number 4. Look at what their average, this was how kids scored on this thing. Out of 9 points, most of them, the average was 2.6 out of all 9 of those points. Now, where did they lose those points? There's the rub, right? That's the tough part to figure out what pieces they lost. Lots of little sneaky stuff I could argue that you could lose along the way. But man, think about it. That's the average. If you want to get a 5, well, you could outscore that 2.6. Boy, I think that it sure just seems that we could do it. Now, the tough part is being able to recognize all this stuff that we did along the way. But That's what the reviews are for. The more you review, the more you're likely to see it. Anyway, okay, so now here we are. Use the data in the table to approximate the rate. Oop, I'm going to stop right there. I'm going to highlight something. What am I on? I'm on squiggle alert. We're going to approximate something. You're going to need some squiggles. In hundreds of entries per hour at which the entries are being deposited at time t equals 6. Show the computation that lead to your answers. All right, so let's talk through this. We want to see how fast they were being deposited. We want to see the rate of change. Okay, how fast were these things getting put in per hour? Hundreds of entries per hour. That's slope, guys. Look, hundreds of entries per hour. Hundreds of entries are our y values. Hours are our x values. So it wants to figure out how fast E of t is changing according to t. That's just a slope formula. So don't overthink it. You got to be on alert that this is a rate. So a rate usually means y prime or something like that. Now let's calculate the rate. Now this is going to be the rate when. Now we shouldn't say y. We should say e prime. At what time? At time equals 6. Squiggle alert. Squiggle alert. Squiggle alert. My squiggles suck. I got to get better at drawing squiggles. So can we figure it out exactly? Nope. We have a data table. So how do we figure out when we have a data table? That's why they say approximately. In this case, I would really only use, you should do this on your own. Pause. You should do this on your own. And if you can't, you should hit yourself in the hand. All right. This is one where we would calculate the slope around that value of 6. So t equals 6 is somewhere in here. Is halfway in between, but I don't know what the y value is. So if they gave me the 6, then I could calculate using, remember how you could do 5 and 7, 6 and 7, or 5 and 6, and they all would be appropriate approximations. I think in this case, the best approximation would be 5 and 7. So that would be E of 7, take away E of 5, divided by 7 minus 5. Now, we are no longer on squiggle alert because these are exact values. So this fraction is going to equal whatever is over here. E of 7 would be 21. E of 5 is 13. 7 minus 5. The beauty of doing free response is that you could stop here. You're allowed to stop if you want to. Stop if want. Actually, I'm going to stop. I want to stop. I don't want to keep going. Why is this still wrong, though? Why would I lose some points? I'm guessing this is a 2-pointer. What did I forget? I don't have any units. So this is the rate of change in hundreds of entries per hour. So I would say this, and then I would just write hundreds of entries. Hundreds. Oh gosh. Hundreds of entries per hour. If you want to go ahead and try to calculate that, it actually comes out, I think, to be 8, which is pretty nice. But yeah, you don't have to. You don't have to. And if you make a little mistake, even with this correct difference quotient, you'd still lose some points. Show the computations. We did all that. So that's an easy one. That's an easy couple of points. If you recognized it, of course. Part B, use a trapezoid sum rule. Hey, a Riemann sums. 4 subintervals. Let's make sure that fits with our table. Do we have 4? So here's 1, there's 2, there's 3, there's 4. Yep, that's good to go. To find the value of 1/8 integral. Now that's a little sneaky. What do they have out in front of this? They threw a 1/8 out there. So let's see. So we want to calculate 1/8, the integral from 0 to 8 of E of t dt. That 1/8 is going to make sense in a little bit, but it's a little sneaky right now. So I'm going to leave the 1/8 out there. Actually, I'm going to do these in, I'll do 1/8. Now I'm timesing by the integral. My bad. Now I'm timesing by the Riemann sum, the trap sum of this integral. So that means what's the trapezoid sum rule? It's going to be a 1/2 of my base 1 times base 2 for each one of these. Can we take out a common height? Do we have a common height? That's a difference of 2. That's a difference of 3. Nope, game over. Difference of 2. That's a difference of 1. So our heights, we don't have what's called equal length subintervals. We have to calculate our height and radius, height and base 1, base 2 differently. So just a reminder, 1/2 base 1 plus base 2 times the height. So I'm going to actually put the height first. I took the 1/2 out, so I don't have to keep writing that each time. So I'm going to do the height times base 1, base 2. So my height, my first height is 2 times base 1 and base 2, so that'd be 0 plus 4. Plus, my next height is 3 from 4 to 13. My next height is 2 from 13 to 21. My next height is 1 from 21 to 23. A couple of things to point out. Notice, you see how the 4s, these are still, remember how when you do the trap rule that you have these things kind of repeat twice? We still have that repeating section. Remember that part? I don't know if you remember that, hopefully, from when we were doing trapezoids, that those two bases end up showing up twice. And I am going to stop. Can I stop? Yeah, I don't care. This is it, man. There it is. I'm done with that. So it doesn't say we have to actually compute it. Now we need to explain what this means. Now the 1/8 comes into play. This is tough. I get it, man. I get it. I don't know how you recognize this, but I recognized it. And so if I can do it, you can do it too. I noticed this 1/8, and that kept bugging me. Like, where did they come up with 1/8? And then I looked at the interval. That's also from 0 to 8. I want you to now think back. What is this thing represent? What is the integral divided by how wide the interval is? Well, hopefully you said it. It's the average value. So 1 over 8 times the integral from 0 to 8 of e of t dt gives the average. Okay, now let's take out the average value and actually talk about when you integrate, what does that actually tell us? So if I integrate how many hundreds of entries there were per hour, that's going to give me the average number of entries in the box at any moment in time, right? If I add up all these numbers, right, 2,300, what does that mean? That at the end of the 8 hours, there were 2,300 entries in the box. Let's talk a little bit more about that. At time 0, there were no entries. At times 2, there were 4 entries. Why does it make sense that there were no entries at time 0? They just put the box out front, right? So 2 hours in, only 4 people had dropped off their entries. But after 5 hours, 400 people had. 1,300 people have. At times 2,100, 2,300 people have done it. So on average, if I took up at the end, there were 2,300 entries. At time 0, there were 0 entries. But if I wanted to figure out on average how many entries were actually in the box, that's what this thing would calculate for us, our average value. So the average value would be the average number of entries in the box. Dang it. Average number of entries in the box in hundreds of entries. Units are a pain here. In hundreds of entries. The number of entries in the box in hundreds of entries from time t equals 0 hours units to t equals 8 hours. Man, those those units just jump off the page to me when I write times t equals, but those other units are sneaky. Those are the ones that I really struggle with recognizing. Don't forget those units. The other units are, I mean, if you forget those, that's on you. This is a little sneakier. Oh man, we got two more to squeeze in here. Uh-oh. All right, part C. At 8 p.m., volunteers began to process the entries. Okay, so that makes sense, right? So from noon until 8 o'clock. That's what the table is telling us. All these, and the box was open and people could try to name their baby elephant. And then at 8 o'clock, volunteers came in and they started to sort out the entries to try to figure out what name showed up the best, or who they thought the best name was. So they processed the entries at a rate modeled. So I'm going to underline something here. Did anything jump out to you as I said that? They process the entries as a rate. This is a rate modeled by this equation. Hundreds of entries per hour. So this is a rate of change. There's my per. That tells me again. From 8 until 12. So how long did they work on these entries? 4 hours. They worked from 8 p.m. until midnight. According to the model, how many entries had not yet been processed by midnight? So if I calculated, so my first instinct was to plug in P of 12. So I wanted to say, all right, so what's happening? P of 12. P of 12 is equal to, and then I typed it into my calculator and I got 8. That was my first guess. Well, wait a minute. What would that mean? That would mean, wait, did I get 8? Let me double check that. So that would be what? 12 cubed minus 30 times 12 squared plus 298 times 12 minus 976. Yeah, 8. And then I thought, wait a minute, that doesn't make any sense. That means that they had only processed 8 cards since they started. I mean, these are the crappiest volunteers in the history of volunteers. That was my first instinct. Well, no, I don't think so. Something's goofy about that. That seemed wrong to me. So I started to think about it a little bit more, and I said, all right, if I want to figure out how many were processed, let's think about what P of T stands for. P of T is the rate at which they're processed. So if I integrate that rate, if I integrate how fast they're being processed over a certain time period, then I would be able to find out exactly how many they actually processed. So I want to go that route. Now, when I was watching Corpy's video, he came in with this right off the bat, but I'm going to save it to the end. So he came in with the final amount right off the bat. I'm going to think about it a little bit differently. So if I integrate from 8 until 12 of P of T dt, that when I integrate that's going to tell me what how many entries were processed total. Now, if you want to, feel free to go do this by hand. This is something I would say would be pretty easy to integrate, but plugging and chugging. This is a calculator permitted problem, so I'm not going to ask my calculator to do this. Or sorry, I'm not going to do this by hand. I'm going to ask my calculator to do it for me. Now, let's see. There's 2 ways you can type this in. You can go right to your Math 9 and bring up your integration function. I'm wondering, because it says in part D, according to the model from part C, I'm wondering if we have to use it again. So that's why I'm going to put it in here instead, because then I can use the Y1 feature. So x to the third minus 30x squared plus 298x minus 976. And then from here, I'm going to go back to this screen. I'm still going to integrate, so I'm going to still need Math 9, but I'm going to go from 8 until 12. And then I'm going to use, remember, alpha, F4, and that brings up Y1. And we're integrating according to X, even though that's a Y. Remember, that equation is based on X. And so what do we get? 16. So what is this telling us? This is telling us, pause and try to think about what this represents. This represents how many entries were processed between 8 and 12 midnight. 1,600, notice it's not 16, it's 1,600 entries processed from t equals 8 to t equals 12. Now that's not the question. The question is, according to the model, how many entries had not yet been processed by midnight? So how many entries were there? 23. Now some people just write 23 here, or some people write 23 with 2 zeros afterward. Which one should we be using? If we're going to use 16 in our calculation, should we do 23 or 2,300? Hopefully you said 23 because that's already in hundreds of entries. So do we have to do like a write-up at the end here? According to how many entries? Nope, we can just kind of say it. So let's just kind of put it all together here. So 2,300 subtract the integral from 8 to 12 of p of t dt is equal to 23, take away 16, which equals 7. 7, right? Nope. Could you put 700? Yes. No, you couldn't, because 23 minus 16 is definitely not 700. So we have to write 7 and then put the 100 with this. Hundreds of entries. I think you could just write 700 entries. I don't know why that of. I don't know if you have to have that of in there. Okay, last one. Here we go. This video. How long has this video been going? Quite a while. I don't have the time up there. According to the model from part C, so that's why I'm glad I typed it in. At what time were the entries being processed most quickly? Okay, so let's try to talk about when we're trying to figure out when they're being processed most quickly is going to be how fast when is this thing changing at its best? All right, what's the highest number for this? What's the maximum? This is another extreme value theorem. We did that a couple examples ago. Or maybe last example, it feels like a couple ago. This is another extreme value theorem. In other words, this is the rate that they're being processed, and I want to figure out when they're being processed the best or the biggest or the highest amount. So I'm going to do the extreme value theorem again, so I need some candidates. So part D. Our endpoints. What are our endpoints? From what hour to what hour? Hour 8 to hour 12. So we've got our... Can I go right to candidates, Chet? So we have what's happening at hours. How fast were they being processed at hour 0? Dang, I fell for it. Processed at hour 8, not processed at hour 0. Because hour 0 would have been way back when they put the box first outside for somebody to look at it. And then processed at hours 12. So those are the endpoints. And now we've got to figure out the other places that you could have extreme values. And those are at the crit values. So the crit values are going to occur where p prime of t equals 0 or dne. So this wouldn't be too bad to do by hand. You could derive this, set it equal to 0, and try to solve it, but why bother? Because we can use our calc. So this is why I'm glad I typed it in here. I've already got the p function in there. Now, can you graph can you graph the derivative of this? And I don't know if I've shown you this yet, but hopefully I did. Yes, you can. So I'm going to go now to alpha, bring up this n derivative. Now look at what it gives us. It says dd. All right, we're deriving according to x. And I want to derive this function here, so I'm going to put in y1. And I want to derive it for which x? I want to derive it for all x's. So I'm going to say when x equals x. And now when I graph, notice you had to turn this one off, so don't get confused. And then it's helpful here, so that's going to be the graph. That's going to give me a graph here of the derivative. And let's just do a quick check. Graph, are you going to appear at some point? There it goes, way over there. Yeah, that makes sense considering I had a crappy window. So let's adjust our window. We're going from 8 until midnight. There's a better picture. And does this picture sort of vibe with what we would think the derivative of a cubic? Yeah, the derivative of a cubic should be a parabola. So this looks pretty good. Now there's two ways for you to figure out, we want to figure out, does this derivative ever equal DNE? No, this is continuous, so this is never. Does this derivative ever equal 0? Yes, it does at 2 places. Now, I would argue that one of these you could eliminate right off the bat because we're trying to figure out most quickly, so we're trying to find a maximum. But you should probably write them both down. This definitely is not the answer because this is where f prime switches from negative to positive. This is a relative min. So if this is a relative min, then there has to be points just somewhere that are bigger than it. So I should be able to ignore this one. But we'll see. We'll check the scoring guide and see if there's anything that fits with that. But I definitely need this one. I need them both. Now there's two ways to do this. I can go second calc, 0, and then move to do the boundaries. You know how we do left bound, right bound? Left bound, right bound. Take a guess. And that finds this number. Now I'm going to write this over here, but I'm going to use my calc to store this. So quit out of this, and I want to just hit store alpha A. That took my last input, or output I should say, and stored it as A. So now I can say T equals 9.183, which equals big A. Now from here on out, I can use big A all over the place. So over here, I can call this P of big A. I don't have to write P of 9 point blah, 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 blah. Now we had this other one, and let me show you the other way that you can find out where this graph intersects. I want to figure out where it intersects the x-axis. I can make an equation of the x-axis, y equals 0. And so that's going to graph it. Now we can't see it because it's on there. And now instead of using the 0 feature, I'm going to use the intersect feature. And I just move a little bit closer, and then all you have to do is hit it 3 times. Boom, 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 and it finds our other one for us. This is another thing that I want to store. So I'm going to quit out of here. That last output becomes my new input, and I'm going to store that as alpha B. Now I still have to identify that 10.816 is what I'm calling B. But when I compute it over here, I can now use B because I've said what B stands for. Okay, we've got our candidates. We now have to figure out who's the biggest and who's the smallest. Now what's nice here is that we still had this function. The original function is in here. I'm going to clear these out. I don't need them anymore. So I can now, I'm going to graph this thing. I got to go from 8 to 12, so my window is still good. I hope it'll let me do it 8 and 12. And we'll find out in a second, won't we? It's still what's going on? Oh, I never turned it on. Doy. Got to actually have that equal sign highlighted. There's our function. Let's trace to 0. God darn it, I was afraid of this. So quit. Make your window a little bit bigger. So I'm going to go from 7 to 13. Annoying. We're done thinking. That thing stopped. Trace to 8. Did I type in 0 last time? I want to see something. Did I screw that up? Did I hit trace 0 or did I hit trace 8? Oh, geez, it didn't. It gave it to me. All right, I bet you I hit 0. So 8 is 0. What's happening at 12? 12 is 8. What's happening at, so I hit trace and then I hit alpha A. And it'll take that A value that we stored and it'll plug it in. And we get 5.088. And then I hit trace again, or you don't even have to hit trace again, but I call it alpha B. That's 2.911. So who's our max? P of 12 equals 8 is our maximum, but we still needed to talk about A and B because those are our crit values, so they're candidates. They're ones that we could possibly have. Now I'm going to read the question again before I write this all up. According to the model from Part C, at what time were the interests being processed most quickly? This is our justification. We don't have to do any more justifying here. We can just jump right to the answer. And our answer is the entries were being processed and I like to use their wording, most quickly. Were being processed most quickly at time t equals 12. Is it hours? I forgot already. Yep, hours. Does that make sense? Yeah, I think so. I mean, why would they be getting processed the quickest at the end of their shift? They probably got good at it, right? So they probably could process them a lot quicker, and then they might have felt some pressure to get them done because they knew their shift was about to end. So there's lots of reasons that seems like a reasonable answer. Let's see if I have better luck finding the scoring guide for this one. So I would go here, just do a quick Google, AP Calc, free response question 2010, scoring guidelines. So we can at least check our answers. Yeah, that's us, right? This is our story. Okay, let's see. Trapezoids, or sorry, all we needed was the answer. Oh man, they didn't even write in the numbers. Look at, we wrote in, we at least put the 21 and the 13 in there. They stopped right after that and they were done. Notice the squiggles though, they got the squiggles there and they have the units, hundreds of per hour. Trapezoid sum, 1 point for the trapezoid sum, 1 for the approximation, and 1 for the meaning. So how did we do? So they wrote theirs out as, so there's the approximation. So they got the approximately symbol. They wrote theirs out as E of 0 and E of 2 instead of, we wrote ours out as 0 and 4. We put the E of 0 and E of 2 actually in it. That's fine. They had it equal. We didn't have to. We got what we needed. We got the points. And then, so it says one is the average number of hundreds of entries between noon and 8 p.m. We said number of entries in hundreds of entries. Oh, that one I'm gonna forget that one when we do these together. But from 0 to 8 hours. They use the actual time. We chose not to. 23. See, this is what Corpy did. He put that in right away. So he calculated it that way. But ours ended up being the same. I mean, I said it eventually, right? We put it in there eventually. We got to the 700s of entries. And then look, there's their justification. Look, their justification. They didn't say any words here. They just did their crit values. They showed why these were crit values because P prime of T equals 0. We said the same thing. P time of equals 0 for these, and then D and E never. Then they made a chart of those values, and we made a chart of those values. And then they said they're being most processed at time. Hey, all right, good job.